Alright, so on the previous video, what we did is come up with a way to calculate the instantaneous rate of change using as a basis the idea of finding the average rate of change. So we combine the definition of the slope, and then we put together this average rate of change and combining with a limit as h approaches 0, and we got the definition for the derivative. So now let's do an example in which we will be able to find the actual value of the derivative at a given point, no longer between 2 points, no longer the average rate of change, but rather the instantaneous rate of change. So what are we going to have? We have that an arrow is shot into the air and its height in feet after t seconds is given by the function f of t equals negative 16t squared plus 880t. The graph of the curve y equals f of t is the parabola that is shown over here to the right. It's this parabola right here, all right? And so number one, let's find the height of the arrow when t equals to 3. So all we have to do in this case is simply evaluate the given function at t equals to 3. So f of 3 equals to negative 16, 3 squared plus 80 times 3. And then, well, this is going to give us, well, 3 squared, which is 9 times negative 16. That's the negative 144 plus 80 times 3, which equals to 40. And this reduces to 96 feet. And of course, we can sort of approximate or verify this from the graph of this function that we have next to it. So after 3 seconds, the y value right here, well, it's somewhere here, 96. It's almost the highest point in the parabola, but not quite. All right. So let's clear this real quick. Find the velocity of the arrow when t equals 3. Notice in this case, they are not asking for the average velocity, but rather the instantaneous velocity. And well, in this case, we're going to use the formula, the limit definition of the derivative here to find the instantaneous rate of change. So in this case, let's write that down. So what we need to do is to find the derivative denoted f prime of t, all right, and this is going to be the limit as h approaches 0, f of t plus h minus f of t. Of course, the original definition calls for x. Well, in this case, because x is replaced with t, well, we're going to change this to t. All right, well, what are we going to do from here? So from here, we will replace t plus h, whatever gives you the letter t, which is one here and another here, and then we are going to subtract the original function. All right, so how are we going to do that? Well, limit as h approaches 0 of, well, negative 16 t plus h plus, not minus, 80 t plus h, and then minus the original function. And be careful here because the negative signs are going to make some effect on each of the terms. So this part right here constitutes the f of t plus h minus f of t. the original function. That's what it does in this case. Well, so, whoops, what did we erase? Yeah. So what we're going to do here is to divide everything by h. Oh, come on. Why is that blue? All right. So we're going to divide this by h, and we will first of all try and simplify and clean up all these expressions. So be careful here. This one multiplies to give us a plus. This one changes to minus. And the one I'm worried about is this t plus h squared. So you might want to recall the formula for the binomial squared. I believe I covered something like this on the previous section. If not, well, when you have a binomial squared, well, if you FOIL, in the end, what you get is the square root of the first term plus 2 times the first times the second, and the square root of the second term. So we can apply this rule of the binomial square to the t plus h squared to get the following. Limit as h approaches 0 of negative 16 times t squared plus 2ht plus h squared plus, well, we can also distribute the 80, and that's 80 t plus 80 h, and then plus 16 t squared minus 80 t, the whole thing over h. I know this one is going to take a lot of another set of distributions, and at the same time what we can do is notice how we cancel these two terms. We can start doing that. Why not? And well, this will be negative 16t squared minus 32ht minus 16h squared plus 80h and plus 16t squared, and that's going to be about it. The whole thing over h, and we can also cancel more terms. These two terms can be canceled. And notice after we cancel those terms, so if we attempt to compute the limit, I mean, we could have done it from the very beginning, but the problem is this h approaching 0, this 0 in the denominator, that's going to cause a lot of trouble. So our goal is to get rid of that factor of h in the denominator that turns it into 0, and we will. Notice we have an h here, h squared, h. Notice the remaining terms, the three terms that survive, in this case, limit h approaches to 0, that's h and h times negative 32t minus 16 times h plus 80. Whole thing divided by h, and see how these terms cancel out. So limit of negative 32t minus 16h plus 80 as h approaches 0. And if we evaluate the limit, so notice in this case we have like two variables at the same time. However, the one for which we are going to make it approach 0 in this case is h. So this term goes to 0. And when we compute the limit, we are left with negative 32 t plus 80. All right. So this is equal to f prime of t. That is the derivative. And well, what does that represent? So we are going to use this this function or this expression, the derivative. So that's the derivative of the function of this parabola. And we are going to use this expression to find the instantaneous velocity. For example, what if I want the instantaneous velocity at t, what is it, seconds or minutes? I believe it's seconds, yes. After half a second. Well, no longer the average rate of change, no longer the average velocity, but actually the instantaneous velocity, the velocity exactly at that point, at 1, at 2, at any time in particular, at any particular time. All right, so, and in particular, they're asking us to find the velocity after 3 seconds. All right, so let's see. So what we do in this case, we're going to use this expression to evaluate at 3. So negative 32 times 3 plus 80. So in this case, we need to compute this value, and that should give us, so negative 2, let me get my calculator here. That's negative 32 times 3, and that equals to negative 96 plus 80. This is negative 16. All right, we get a negative 16. And in this case, well, need to feet per second, because this is a velocity. Velocity is distance over time, feet per second. Okay, let me write this 16 more neatly. Negative 16 feet per second. All right, now let's see. On the next page, they're asking us to find the slope of the tangent line to the curve at t equals 3. So this is what's going on. So we go to x equals to 3. We look for the corresponding y value. So at this point, there is a tangent line. And in this case, notice it has a negative sign, it has a negative slope, and therefore the value of the slope has to be negative. And in this case, well, in this case, since the slope of the tangent line, slope of tangent line equals to derivative at the point or at a given point. All right, so in this case, well, the slope is the same. Slope m equals to negative 16. Notice in this case, I'm not going to write feet per second because they're not asking me for the velocity, but rather they're asking for the value of the slope, which in this case is negative 16. Now find the time it takes the arrow to reach its peak. That is, to reach the maximum height. Alright, so how are we going to solve this problem? Well, so number one, see for example how at this point, well, there is this line with whatever slope, then is this line with the slope, and then that line with this slope. No, not like this, maybe like this. However, we are interested on the value for which this on the value at this point at its peak. That is the maximum height. And in this case, well, if you look at this point, there would be a horizontal tangent line. And well, how are we going to find that value? So in order to find that value, we need to know what the slope of a horizontal line is. In this case, m, the slope is equals to 0. All right. So what do we have to do in order to get that value? So find the time it takes the arrow to reach its maximum speed. Okay, uh, so in words, find the time when the velocity is equal to 0. When it is equal to 0, we're going to get that maximum height. That is, set the derivative, f of t, set it equal to 0. And in this case, what did we get for the derivative? We got negative 32t plus 80. Set it equal to 0 and solve for the variable t to find the time where the arrow reaches its maximum height. So in this case, I'll divide both sides by negative 32 to get t equals, well, 80 over negative 80 over 32. That reduces to 5 halves, which is in decimal 2.5. 2.5 seconds. All right, let's verify that with the graph that we had over here. So let's see, let's go let's go to that point where the maximum is, and the time, well, yes, it's exactly in the middle between 2 and 3, which is precisely 2.5. All right, so I know this process of finding the derivative of a function it's long. It might be painful, but there's something that we have to go through in order to before we are able to use the differentiation rule. Well, I mean, if you already took a class like this before and you know what those rules are, you will see that this problem could have even solved in a way shorter time. However, this is something that we still have to do anyway. And this actually concludes this section 2.2. We're going to move on to next section 2.3, in which we are going to find derivatives of functions, but in this case we're no longer gonna interpret it as finding the instantaneous rate of change or applications like this. We are just going to differentiate functions, and to do that, well, let's take it to the next video.